Hello, I'm Philip Nelson, and I want to tell you a little story about modeling using physical ideas. And you may say, doesn't sound like physics to me, but look, here's a pendulum. If there's a pendulum, it has to be physics. So bear with me a little bit, and you'll see what I mean when I say that that's relevant. So before we get started, I wonder if this sounds at all familiar to you. You say to yourself, man, all the dynamical systems I ever learned to solve in physics class, they're all linear systems. If you don't know what I mean, you will in a minute. But everything interesting and important in the world seems to be nonlinear. If you don't know what I mean, you will in a minute. So must I wait until somebody tells me how to solve every damn complicated equation in all of physics before I can get down to doing something useful with my life? If only I had an assistant who could do that stuff for me. Well, all right, what I want to say today is, first of all, I want to give you a little insight into how physicists think about nearly every problem, which is whenever possible, graphically or pictorially. And I also want to introduce you to one assistant who can do things for you, of many. Along the way, I want to demonstrate some skills and habits that come up all the time in modeling problems. And so let's get going. We are going to start with this humble pendulum, so you'll know that it's really physics, but I'm just letting you know we'll go beyond that. So you want to understand how a pendulum is working. I guess you start with F equals ma. But before we go any further, what if we're not completely sure that F equals ma is the right equation? What if we're not completely sure that we remembered it properly? Well, physicists' first impulse is always to make sure that the units make sense. So you look up in a book, you see that force is measured in newtons, mass is measured in kilograms, acceleration in meters per second squared. Kilograms times meters per second squared, it turns out to be the same thing as newtons. So this formula says newtons equals newtons, and therefore it might be an okay equation. It's not an obviously wrong equation, okay? It's just not the equation we need for this problem because this is pinned at one point. This is a rotary problem. So we need the angular version of Newton's law, which is equally simple when you write it down. It says torque is equal to moment of inertia times angular acceleration. Okay, but again, before we go any further, this is a little bit less familiar. We better check the units. So what is torque? Well, it's force times the moment arm times sine theta. So its units have got to be newtons times meters. There's the length of that arm is meters. What do we got on the other side of the equation? Well, when you look up formulas for the moment of inertia, it's kilograms times meters squared. So I put that down there. Angular acceleration, well, that's radians per second, but a radian, what are radians? It's circumference divided by a radius. It's meters divided by meters. It has no dimensions. So angular acceleration is just nothing per second squared, which what I've written down there. So all right, do those units match up? Yeah, kilograms meters squared per second squared is the same thing as kilograms meters per second times squared times meters. So yeah, the units work out. It's a potentially reasonable equation. Maybe we remembered it without any mistakes, but we still got to unpack it. It's kind of complex, kind of compact, has a lot of meaning in a very small number of symbols. So let's just remember, before we get into angular acceleration, there's angular velocity. How fast is angle changing? There's an angle which this makes relative to hanging straight down, and that's what I'm going to call theta. It's that Greek letter. But there's an angular velocity, which is how fast theta is changing per time, which I'm going to call omega, another Greek letter. That's the lowercase omega, not the one you see in fraternity names. So to say that omega is the angular velocity is to say it's the rate of change of the angular position, or in each instant of time, the angular position changes by an amount proportional to omega. So that's one equation. It's a simple one, but we need a little bit more. We need to know a formula for how is angular velocity changing in time. That's the angular acceleration. But Newton's law tells us that it's torque divided by the moment of inertia. That's how much angular velocity changes in every unit of time. And furthermore, for this pendulum, we got a formula for the torque. There's a force of gravity always pointing straight down. There's the moment arm, which is about half a meter here, but there's also the sine of the angle between them. So altogether, it's torque is mass times the acceleration of gravity, that's force, times r, that's about half a meter here, times the sine of the angle, that's coming from the formula for torque, that's torque, divided by moment of inertia, mr squared, and that's how much angular velocity is changing per unit time. That's our equation of motion. Now, right away, you see that the masses cancel from the numerator and denominator. That simplifies things a little bit. What about units? Always check the units. Well, angular velocity is radians per second. That's inverse seconds. On the other side, dropping the kilograms, you got meters per second squared. That's the acceleration of gravity, times meters. That's the moment arm, divided by meters squared, because the length of the rod, the length of the string squared appears in the denominator, times seconds for delta t. And yes, inverse seconds is equal to seconds to the -2 times seconds to the 1. So yeah, we haven't introduced any new typographical errors. If you do this on every single step of your derivations, you'll catch all of your errors very quickly and fix them before making any further progress. Then probably you've seen this in courses before. Probably you've heard people say, yeah, but for small angles theta of just a few degrees, sine theta is about equal to theta, so we can simplify the equation by replacing sine theta by just theta itself. Yeah, that does simplify the equation. I'm going to criticize that in a minute, but for now, it's good. But we still got equations that are more complex than they need to be and have too many distractions that we ought to get rid of. Okay, why is that? Well, there's two parameters. There's the acceleration of gravity. This whole thing would act differently on the moon. It would act differently on Jupiter. It would even act differently on top of a mountain, because it depends on this parameter, the acceleration of gravity. Then there's the length of the string, r, that's another parameter in there. It would act differently if the string were longer or shorter. So this isn't really one set of equations. This is a whole family of sets of equations for each value of the parameters. So that's kind of complicated, potentially, but at least those two parameters, they only enter in one combination. The only thing that enters there is the quotient g divided by r. So it looked like two parameters, it's really one parameter, but I want to tell you, no, it's really no parameters at all. We can get rid of all the parameters just by noticing that r divided by g is seconds squared. So if I take the square root of r divided by g, I get a natural time scale associated to this system. And there's nothing special about measuring time in seconds. Instead of measuring time in seconds, we should measure time as multiples of that natural scale. Let me call that t0. And then I'll introduce a dimensionless variable, t bar, which is just time divided by t0. It's time measured in units. How many t0s have gone by? That's a dimensionless quantity. And similarly with the angular frequency, except I got to multiply by t0 to make all the units go away. So now I got two dimensionless quantities, t bar and omega bar. Just everywhere I see a t or an omega, I'm going to substitute into my equations these expressions. So wherever I see a t, I'm going to replace it by t bar times t0. Wherever I see an omega, I'm going to substitute it by omega bar divided by t0. And that will recast the equations in terms of these dimensionless quantities. So all right, delta theta, that doesn't change. T0, delta t becomes t0 delta t bar. On the other side of the equation, omega becomes omega bar over t0. And now I see that there's a t0 on each side of the equation. I can just cancel it out, and magically t0 is gone altogether from that equation, and from the other equation as well. So cleaning it up a little bit, my equations have become now about as simple as they could possibly be. The time rate of change of theta is omega. The time rate of change of omega is minus theta. Okay, no parameters remain at all. At the end of the day, if I want to turn back into seconds, then I'll need to know what's the value of t0. But while I'm doing the hard, heavy lifting of solving these equations, it's not there distracting me. Okay, system has no parameters left at all. It's just really one set of differential equations. Okay, there they are again. And we can even guess the solution. After all, even if you hadn't taken a physics course before, this is going back and forth periodically in time, and you know some periodic functions like sine and cosine. Those are nice, smooth periodic functions. This is cos of t bar. You see at this top, it's level. That means its time rate of change is 0. Then it starts sloping down. Its time rate of change is negative, gets maximally negative, then levels off again until it's 0 halfway through, and then starts rising. Now its time rate of change is positive. So I've written all those things in the graph below. Starts off at 0, goes negative, comes back up to 0, goes positive, comes back down to 0. This is the time rate of change of the first graph. And my first equation says that must be the angular velocity. It's the time rate of change of the angle. But now for the second equation, we need to know what's the time rate of change of the angular velocity. We got to do the same thing to the second graph. Well, it starts off sloping down. That's negative. But then it levels off to 0, so that's 0. Then it starts sloping up again, that's positive. And we build up step by step this curve. Starts negative, goes up to 0, becomes positive, back down again. Okay, that's the time rate of change of the second curve, the time rate of change of omega. And yeah, it works because the third graph is minus the first graph, which is what the second equation of motion says it should be. So just by guessing, we found that cosine of t bar is a solution to this equation of motion. It's periodic in time. It repeats every time t bar increases by 2 pi. So what does that mean in terms of seconds, in terms of ordinary time? Well, you got to know what that time scale t0 is. You got to take 2 pi and multiply it by t0. So I measured this string. It's 55 centimeters long, about. And so we get this prediction for what the period of this pendulum should be. Let's just see how we're doing with that prediction. I'm going to start it going. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, that was 15.1 seconds for 10 oscillations. That's about 1.5 seconds per oscillation, just what the math predicted. So that's cool, but I got to throw a little damp water on that. I started out with a initial angle of about 20 degrees or something. Let's try it over again with an initial angle more like 90 degrees. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Uh-oh, that was almost 17 seconds. Our math was predicting that the period of this thing should not depend on how much mass there is. I didn't change that. Shouldn't depend on how big my initial swing was, but it did depend. For small values of the initial angle, I was getting an accurate prediction, but for big values, I wasn't. So sorry about that, Galileo. Let's keep that in the back of our minds as something we got to deal with. Okay, well, I can tell you right now what's going on. We were so happy we found an exact solution, but it was an exact solution to an approximate equation. When we said sine theta is about equal to theta, yeah, that's true for 20 degrees, but it's not at all true for 90 degrees. Okay, this problem is a little more complicated to do exactly for large amplitude. Okay, those equations at the top of the screen, they're linear equations. d theta dt is linear in omega. d omega dt is linear in theta. If I replace that theta on the right by sine theta, suddenly we got nonlinear equations, and it's a more difficult problem, and how are we going to solve it? It doesn't have any simple solution that I can just write down in a line. So we got to start over. We got to think differently. We got to figure out a way to address problems like that. And we have to get away from this urge to find an exact, complete solution, and instead try to figure out what's going on. Okay, so physicists have developed a way of thinking about what's going on. What I need to tell you about the state of this system. Well, it's not enough just to tell you what the angle is, because I could release it from rest, or I could release it from not at rest. So to tell you the state of this system, I have to tell you two things. I have to tell you where is the bob at the moment we're talking about, and how fast is it moving. So there's a whole two-dimensional plane of initial conditions for this thing. Any point on this plane, one axis is where, and the other axis is how fast. Once I tell you those two things, then I got a little arrow on the plane. Drew a little arrow on the plane. My two equations, if you know what the state is, one of my equations tells you how is omega just about to change. The other tells you how is theta just about to change. What's going to happen in the next instant of time. I drew a little arrow on the plane indicating those, and each point of the plane has its own separate arrow. So these arrows are a vector field. They're telling me what the system is just about to do in the next instant of time. And all I got to do to predict for you how the thing is going is to run my finger along these arrows. Start anywhere, follow the nearest arrow. Wherever it goes, follow the arrow at that location, keep going. And you can see that I'm going to go around and round in circles. This is called a phase portrait. It's what I've been doing so far with the approximation that sine theta is about equal to theta. And sure, each of these vectors is perpendicular to a line from the center. That's what those equations of motion were telling us. And when you follow them, you get nice circles. Now, before I leave this picture, I'll just point out there are two interesting sets of points on this plane. There's a set of all the points for which theta is not about to change. Okay, theta is not about to change if the angular velocity is 0. So the locus of all the points where the angular velocity is 0, those are the points where theta is not just about to change. Therefore, the arrows are all pointing vertically, up or down. They don't have any sideways component because at this moment in the trajectory, theta is not changing. Okay, a line like that is called a nullcline. That's one of the nullclines. And then there's another nullcline, locus of all the points where omega is not about to change. Omega is not changing down at the bottom of the swing, and that's what I've drawn here. Those are the locus of all the places where the arrows are horizontal, don't have any vertical component. That means that these are places where omega is not changing, no acceleration. Yeah, of course, when you're right at the bottom, the force of gravity is pulling straight down. It's not tending to make you speed up or slow down. Okay, so here are the nullclines, and when they intersect, that's the point or points where nothing changes at all momentarily. Okay, when my bob is hanging straight down and motionless, then it's going to stay that way. That's the intersection at omega and theta both equal to 0. Okay, so what's so great about the phase portrait is that it's no problem to incorporate a more realistic and more accurate equation of motion. So what if sine theta isn't approximately equal to theta? Well, I'll just draw the phase portrait over again for bigger values of theta, put the arrows on it again, and run my fingers around the arrows. And it's still going to be periodic motion, of course, but these are not circles any longer. Up close to the origin for small angle deviations, they're circles. But as you get away from that, they get to be kind of squashed circles. But whatever they are, you can follow them with your finger and you can figure out what the motion is going to be. You can even ask your assistant computer to find out how much time elapses in one orbit and correctly find that result that we just found, that deviation from always having the same period that you get at large angles. Okay, when I said my assistant, I had a computer draw these pictures. I didn't draw them freehand. It's not that big a deal. So we've got the insight that we wanted into the qualitative behavior without actually having to solve the difficult equations. Adding the nonlinearity didn't really change the character of this particular system all that much. The nullclines are still what they were before. So yeah, here's what I already said. Sorry, Galileo. When theta is small, then it's a sine theta is starting out linear, looks a lot like theta. The blue and the orange curves track each other. But when theta starts getting like as big as a radian, then those two graphs deviate from each other. We now know how to handle that. But now we know how to do many other problems as well. What about a pendulum swinging in some more complicated plane? Like here's one where it's going around in circles. And we can do problems like that with higher dimensional phase portraits. What if there's friction? It's no problem to add friction. I just add another term to one of the equations of motion saying that there's a force opposite to the velocity proportional to the velocity. And here's the phase portrait. And I can draw your attention to a couple of things here. When this bob, if this whole thing was immersed in some viscous fluid, then it would slow down and finally come to a stop, of course. And depending on what its velocity is, if its velocity is high, then there's a lot of friction, and that can even counterbalance gravity. So some of these arrows here are saying things like that. So here's an arrow that's tipping upwards. The angle is positive. Gravity is trying to reduce the angle, but friction for high positive angular velocity, friction is going in the other direction. Up here, there's an arrow that's tipping down. Friction is dominating over gravity at that one. And right at the sweet spot in between them, friction and gravity are exactly balancing. And this vector is horizontal. So I already gave a name to the locus of all the points where the vectors are horizontal. I called it the nullcline. So this orange curve, this S-shaped orange curve, is one of the nullclines. The other nullcline is unchanged. If omega is 0, that means theta is momentarily not changing. That nullcline didn't change. But there's two nullclines, and now we can look for their intersections. And that big green dot there is one of the intersections corresponding to hanging straight down, motionless. Yes, of course, obviously that's a stable fixed point. But if this wasn't a string, if it was a rigid rod, there'd be another fixed point up here where you're heading straight up. That's the red dot. Of course, there's a big difference between those. This one is stable. If I give you a little push, then friction eventually brings you to rest. The other one, if I give you a little push, then you swing through a half a revolution. So you can learn a lot from this pictorial language, even about systems that are kind of complicated and for which you don't know, I don't know even, any analytical solution. I don't need to know. I know what's going on. That's what the phase portrait is telling me. But I didn't really want to talk to you about pendulums today. I know it's far-fetched, but just as a hypothetical exercise, imagine that some new virus appears and that nobody on Earth is immune to it at the beginning. What's going to happen? And what could be done? Well, maybe you've heard about epidemic models. I can imagine a simple illness like strep throat, where you get it, you're sick for a while, during your illness you're contagious, then you get over it, you're not contagious anymore, but you could get it again later. Okay, that's the strep throat model. I'm going to divide the population into two boxes. One box is all the people who are susceptible. That means they haven't got it at the moment. And the other box is all the people who are infective. And then I can draw some arrows between the two boxes. If you're susceptible, you might get infected by an infected person and leave the susceptible bin and join the infective bin. That's what that lower arrow pointing to the right is saying. Okay, but that requires an interaction with an infected person, which is what the dashed line is saying. And the plus sign means that more infective people means greater probability per unit time that you'll do that transaction. And the infective people, eventually they get better, they join the susceptible pool. That's what the upper arrow is saying. That cartoon with those two boxes and those arrows, I can turn that into equations. I can say the time rate of change of the fraction of the population that's susceptible has a negative piece because that lower arrow is pointing away from the susceptible bin. The fraction who are susceptible is going down at some constant times the fraction of people who are susceptible times the fraction of people who are infective. So that's a nonlinear term. Instead of making a new independent variable for the infective peoples, I just remember that if everybody is in one of those two bins, then the fraction who are infective is 100% minus the fraction who are susceptible. That's what the first term is saying. And the second term is saying there's some other probability per unit time that a infected, therefore infective person will recover. So you take the fraction of people who are infective, you multiply by that other constant, and that adds to the susceptible pool. Those are people traveling on the line pointing to the left in this figure. So I can write a phase portrait describing this system. It's kind of simple because it's only one variable instead of two variables. But I can do better than that. An illness like COVID is a little bit different. After you've gotten COVID, you are then not infective for a while. You are recovered and not susceptible for a while. Yeah, okay. With COVID, we now know that you become susceptible again after a while, but some illnesses, you can actually have a very long-term immunity. So I just need to make a third bin. There's a bin of susceptible people who have not got it yet. There's a bin of infective people. And there's a third bin of recovered people. And there are 3 different fractions of the population, but they still all have to add up to 100%. So I don't really need to have 3 variables. The fraction recovered is just 1 minus the susceptible minus the infective. So there's 2 variables. I have a 2-dimensional phase portrait, but I can write down the same kind of equations. I can say the time rate of change of susceptibles is some constant times the product of how many susceptibles there are times how many infective peoples there are to infect them. The second term isn't there because in this model, people who recover permanently. They don't go back into the susceptible bin, they go into the recovered bin. But then there's another equation, the time rate of change of infective people has a positive bit. Every time you get infective, you join the infected bin, that's a positive contribution. And then there's a negative contribution for the recovery. So all right, that still looks like a family of equations with 2 parameters called lambda and gamma, but secretly I can do the same trick as before and reduce it not to 0, but to 1 parameter. I'll introduce the ratio of those called the basic reproduction number, which I put at the top of the slide, and recasting everything in terms of that, I got a 1 parameter family of equations. Okay, there's some equation of change for the susceptible population, there's some equation of change for the infective population, and I don't need to deal separately with the recovered population because it's tied to the other 2. Okay, that's the model called SIR. It's got 2 dynamical variables and 1 parameter describing it, and we can write a phase portrait. Okay, there's a phase portrait if the value of R0 is equal to 3. I just drawn some arrows on the plane expressing what those equations are saying, and if you look at the lower right figure, that's when the susceptible fraction is 100%. That's when a naive population is first encountering this pathogen. 100% of them are susceptible, except for that 1 person who's sick. And I can just run my finger along the arrows, follow the arrows, and well, you can see that I whoosh around and end up at the lower left of this figure. And that, I say, is not a good thing. Why is it not a good thing? If the susceptible fraction ends up at 0, that means that everybody in the whole population got sick. Okay, and some of them might die. So this is something we don't want to happen. Things look totally different if we have a different value of the basic reproduction number. If that parameter R0 is less than 1, if it's 0.8, and you start in the lower right corner, then you crash down onto the axis at susceptible equal to 0.8, and hardly anybody wound up getting sick. The whole outbreak died off with most of the people never having gotten it. Well, that makes sense. A small value of R0 means quick recovery or poor transmission. Okay, but I can say those things. I can't get those computers to, I can get my computer to say those things a little bit more precisely. I can get it to run its finger, and that's what these black curves are. And yeah, sure enough, if you start at the lower right-hand side of this graph, you end up at the lower left-hand side of the graph if R0 is big. Whereas if you start at the same place, you end up close to where you started out with the whole outbreak dying off if R0 is smaller. And even just a little bit smaller than 1 is enough. Okay, that's interesting news. And I've written the nullines in orange. You can work those out for yourself. Does it work? Well, here's some actual epidemiological data about a measles outbreak in a population of people, some fraction of whom refused to get vaccinated for measles. Okay, and well, I've written the predictions of that model. I've got a computer to solve those equations for various values of R0. And well, this orange one doesn't really hit those high points. And this red one overdoes things and overshoots the high points. But the green curve is pretty successful. So what have I done? I've figured out the value of a parameter that I didn't know by varying it and seeing which most successfully accounts for the data. So there are a couple of things that I want to say to you about this graph. First of all, real data don't fit models perfectly because reality is more complex than a simple model. So there was something going on at the beginning of this outbreak that this model isn't capturing. I don't know what it is. Real data are not as pretty as fake data. For one thing, real data has some random fluctuations. There were only fewer than 3,000 people in this whole population, not an infinite number. Still, nevertheless, a model may capture the main trends of a real system and tell us some interesting insights, like the effect of some kind of intervention, like quarantining people, for example. Usually, how important is quarantining people? Does it make a big difference? Does it make a little difference? This is the sort of thing that you can run hypotheticals in models to get answers to questions like that. Usually a model is actually a family of models with some unknown parameters that you have to fit to the data. And real data generally have these fluctuations, as I mentioned. There's some scatter in those points. We may need to incorporate those into our model. Okay, we can build on to more elaborate and more accurate models. We now know that after you've gotten COVID, you can, after a while, get it again. So you can just add a new arrow, have the same 3 bins as we had before, but there's some probability per unit time to transition out of the recovered and back into the susceptible bin. And that adds another parameter to the model and adds a little more realism. And interestingly, in that model, when you write the phase portrait, you start down at the lower right, follow these things, you end up at that green dot, which is not quite on the bottom axis. That corresponds to a state where a small fraction of the population is always susceptible, about 1/3 of them in this case. People keep recovering and becoming susceptible again and getting it all over again. This outbreak is never completely over. It's called endemic behavior. But if you can do something to reduce the basic reproduction number, you can almost eliminate that. You can get all those arrows to curve back to the starting point, and if R0 is smaller than 1, you can eventually eliminate this whole illness. Okay, so that's interesting. So of course, I've only barely scratched the surface here, but I told you about a simple dynamical system that was obviously physics. We learned some lessons about how to understand what its qualitative behavior is without exactly solving it, which was important because real systems are typically nonlinear. Then we applied it to some biological system that happens to be of really great interest right now. So now that it's too late, I'll have to admit that I've shown you how to solve nonlinear differential equations. And it wasn't so bad with an assistant who can make the pictures and the pictures deliver the insights. Okay, my favorite assistant right now is Python because it's free and open source, and there are various books that'll teach you how to use Python. You can learn more about epidemic modeling at websites like this one, and thanks very much for your attention.